Hello, today I want to talk with you about NeuroAI uh, and NeuroAI Grand Challenge the Embodied Turing test. And we will also catalyze next generation artificial intelligence through NeuroAI. So grab your coffee or tea and we are starting. In the next few years, the artificial intelligence is going to change our society and economy in big ways, just like computers did in the past, but probably even faster. This AI wave is exciting because it can spark new levels of creativity and economic growth by taking over jobs that are either too risky or dull for humans. Yet, to fully tap into AI's promise, we need to make it act and think more like humans. Studying the human brain has always pushed AI forward, helping it get better, and seeing that we and animals are good at seeing, learning from rewards, handling objects, and using language. The journey of AI started a long time ago when scientists first tried to figure out how our brains work. The design of today's computers, for example, was influenced by what John von Neumann learned about the brain back in the 1940s. The breakthrough work on how cats see the world led to the development of deep learning networks, which are a big deal in AI today. And looking at how animals learn help create a reinforcement learning, a technique that teaches AI through rewards. Now, with AI evolving so fast, some people think we are close to creating machine as smart as humans or even just a smart mouse. But the truth, we still have a long way to go. Even the experts working on AI say we need some big discoveries before we can create AI that can truly do everything a human or animal can. Why AI can beat anyone at games like chess or Go, it still has trouble with new or unexpected things. Imagine trying to take a robot to walk over to a shelf, grab a chess set it up, and actually move the pieces during a game. Or think about tasks we might find simple, like building a nest, picking berries, or taking care of babies. No machine can do these things yet. Even a 4-year-old child can do stuff that today's AI finds super tricky, like moving around in the world and handling surprises. Some people working on AI think that just making our current AI bigger and more powerful won't solve these problems. They believe we need to learn more from how animals and humans naturally think and act to make AI smarter. For a long time, the cool stuff AI can do, like recognizing images or learning through trial or errors, was inspired by studying. Even now, some new AI ideas come from looking at how our brains focus on different things, but these ideas are often old news. Nowadays, we don't mix brain science and AI as much as we used to, and we are missing out because of it. In recent years, scientists have learned a ton about the brain, and there is this new era called NeuroAI that's all about combining brain science and AI. The hope is that by understanding the brain better, we can make AI that's as smart, as adaptable as humans. This requires a lot of researchers who know both about AI and how the brain works. It's time for a big push to figure out how intelligence works in nature and use those secrets to make robots and computers programs that can think and learn like we do. We often think about intelligence as the ability to think deeply and reason about complex stuff, which seems very human. But actually, the real basics of being smart, like being able to adapt, to be flexible, and figure stuff out from just a little bit of info, are things that even simple animals can do. These skills come from very basic brain circuits that animals have been using for millions of years to move and sense the world around them. A smart person from the past, Hans Moravec, One said that thinking deeply is a pretty new skill for humans, maybe only around for 100,000 years. But the skill works so well because skill works so well, yeah, because it's built on top of this much older and super strong skills that we don't even notice we have, like moving the same and sensing. This means that if we want to make AI that's really smart like humans, a big part of the job is to make AI that can see, hear, move, and interact with the world as well as animals do. Once we can do that, making AI that can think like humans might not be as tough. The cool thing is we can learn a lot about how to do this by studying animals like rats, mice, and monkeys. Scientists already know a lot about how these animals move and sense the world, and this knowledge can help us make better AI. So focusing on these basic skills that all animals have might be the key to making AI that's truly intelligent. Back in 1950s, a smart guy named Alan Turing threw up a game to see if machines could act as smart as human, just by talking. This game, now called the Turing test, has a chat with both a person and a machine that's been trained to chat back like a human. Turing didn't worry about whether the machine could actually think. He figured if it could chat like human, that was enough to consider it smart. For a long time, no robot or computer could pass this test and truly trick us into thinking it was human. But nowadays, we have these super advanced AI systems that can hold a pretty convincing chat, making us think they're smarter than they really are. However, even these advanced chatbots struggle with understanding cause and effect, or the basic common sense stuff learned by interacting with the real world. So while they might seem smart because they can talk a good game, they don't have the same kind of smarts animals or humans do, like being able to see, move, and figure things out about the world around them. We therefore propose an expanded embodied Turing test, or one that includes advanced sensory monitor abilities. Watch this image. The spirit of the original Turing test was to establish a simple qualitative standards against which our progress toward building artificial intelligence machines can be judged. This embodied Turing test would benchmark and compare the interactions with the world of artificial systems versus humans and other animals. Similar ideas have been proposed previously. However, in light of recent advances enabling large-scale behavioral and neural measurements, as well as large-scale simulations of embodied agents in silico, we believe the time is ripe to instantiate a major research effort in the direction. As each animal has its own unique set of abilities, each animal defined its own embodied Turing test. An artificial beaver might be tested on its ability to build a dam, and an artificial squirrel on its ability to jump through trees. Nonetheless, many core sensory monitor capabilities are shared by almost all animals, and the ability of animals to rapidly evolve the sensory monitor skills needed to adapt to new environments suggests that these core skills provide a solid foundation. This implies that after developing an AI system to faithfully reproduce the behavior of one species, the adaptation of the system of other species, and even to humans may be straightforward. Below we highlight a few of the characteristics that are shared across species. Yes, animals engage their environments. Animals are amazing because they can move around and interact with their world in a smart way. Right now, even with all the cool progress in tech and robots, we are not quite at the point where robots can move and handle things as well as animals cannot, even in computer simulations. But studying brains can give us some clues on how to make robots that can move and act more like animals. Neuroscience tells us about special ways that brains are organized, which we might be able to use in robots to help them move and interact better. For example, brains have this neat trick where some parts can do their own things about always needing orders from the topmost parts. And there are ways that brains get quicker at moving, and uh, the more they do, moving from having to think hard about it to just doing it automatically. If you use these brain tricks in designing robots, they might get better at seeing the world, deciding what to do, moving around, and using their robot hands to do delicate tasks. Also, by looking at how brains control muscles for small tasks, we might get ideas for making robots that can plan their movements better. So basically, learning more about how brains help animals move could teach us how to make smarter robots. Let's talk right now about animals behave flexibly. We want to make AI that can do tons of different things, just like animals can. And right now, AI can beat humans at video games by just looking at the screen and the score. But if you change the game a little bit, AI gets all confused and doesn't play well. That's because AI doesn't really get what's happening in the game. It doesn't understand the story or the physics behind things. Like a self driving car might freak out over a plastic bug flying by because it doesn't know it's just a bug and not a big deal. For AI to work well in our crazy, always changing world, it needs to be able to handle new stuff it's never seen before, using what it knows about how things usually go. This is something animals are really good at. They're easy born knowing what to do or they figure it out super fast, all thanks to being part of the real world and learning from it. Animals don't start from zero and then learn everything from scratch. They don't need a ton of examples to learn something new. But AI right now isn't that good at doing things this way. There are some cool tricks in machine learning trying to help AI learn like this, but none of them are as good as what animals can do yet. So we think if we can figure out how animals' brain let them be so smart and flexible, it could really help make AI better. Basically, we can learn a lot from how animals and their brains work because evolution has been working on this for a super long time, making animals really good at dealing with all kinds of situations. One important challenge for modern AI that our brains have overcome is energy efficiency. Training a neural network requires enormous amount of energy. For example, training a large language model such as GPT-3 or 4, it requires more 1000 megawatt hours, enough to power a small town for a day. Biological systems are, by contrast, much more energy efficient. The human brain uses about 20 watts. The difference in energy requirement between brains and computers derives from differences in information processing. First, at an algorithmic level, modern large-scale ANN, such as large language model, rely on very large feed-forward architectures with self-attention to process sequences over time. ignoring the potential power of recurrence for processing sequential information. One reason for this is that currently we do not have efficient mechanisms for credit assignment calculations is recurrent networks. In contrast, brains utilize flexible neural architectures that can solve the temporal credit assignment problem with great efficiency. Uncovering the mechanism by which this happens could potentially enables us to increase the energy efficiency of artificial systems. Alternatively, it has been proposed that the synaptic dynamics within adjacent dendritic spines could serve as a mechanism for learning sequential structure as theme that could potentially be efficiently implemented in hardware. Second, in implementation level, neural circuits differ from digital computers. Neural circuits compute effectively despite the presence of unreliable or noisy components. For example, synaptic release, the primary means of communication between neurons, can be so unreliable that only 1 in every 10 messages is transmitted. Furthermore, neurons interact mainly by transmitting actions potentials like spikes and synchronous communication protocol, like the interactions between conventional digital elements. The output of neurons can be viewed as a string or of zeros and ones, but unlike a digital computer, the energy cost of one is several orders of magnitude higher than that of 0. Let's talk about a roadmap for solving the embodied Turing test. How might artificial systems that pass the embodied Turing test be developed? One natural approach would be to do so incrementally, guided by our evolutionary history. For example, almost all animals that engage in goal-directed locomotion. They move forward some Okay guys, I think about roadmap for solving the embodied Turing test, also what we need, and another topic, for example, we will talk about synapse on a chip in the next video in our second part. So thank you so much for staying with me for today.